Now we'd like to talk about exponents, roots and radicals. So this is all about taking some number and raising it to the power of another number. Now this is quite a complicated thing in general, and you've got to be careful about definitions. So in this first video I'm going to really carefully unpack what exponents mean, what roots mean, and what radicals mean. I should say though that throughout this whole lecture everything is going to be just real numbers, right? So those of you who have heard of the complex numbers, we're not going to touch them at all. So throughout this lecture, all numbers will be real numbers. So no weird complex numbers if you've heard about those. As I've said a few times before, this course is only about real numbers, nothing to do with complex numbers. So I want to define what exponents mean. I want to go through this pretty carefully. So let's start off with kind of a simple question. What happens when we repeat addition or multiplication? So if I repeatedly add a number to itself, what happens? So let's do a few examples. So first of all, let's imagine adding 2 to itself. A bunch. So imagine I do this and we'll do 5 times. So 5 copies. So what do I get? Well, I suppose I could invoke the distributive law if I wanted to, if I'm going to be fancy about it, bring out a factor of 2 from everything, and I would get 1 plus 1 plus 1 plus 1 5 times, multiplied by 2. So this is the distributive law. So distributive property. And what's that equal to? Of course, 1 added to itself 5 times is 5. So 5 times 2, which is 10. And let's just take a moment to observe that this is just multiplication. So more generally, what do I see? More generally, what we have is, well, if I was to take a number b and add it to itself, let's say n times, what do I end up getting? I end up getting n times b. This is basically how you define multiplication, at least for positive whole numbers. So what's the conclusion? The conclusion is repeated addition is multiplication at the end of the day. So let's make sure that's written down. Repeated addition is just multiplication. So let's make sure that's pretty carefully highlighted. Okay, so nice. Of course, multiplication in general is more complicated. This really is only multiplication by positive whole numbers. Multiplication by a half or a quarter, it's a bit more of a complicated thing, but repeated addition is very simple multiplication. Okay, so let's do an example now, not with repeated addition, but with repeated multiplication, and let's see what happens. So let's do the same thing. Let's do 2 times 2. I should write it in my dot notation. So 2 times 2 times 2 times 2 times 2. So again, we're doing 5 of these, is that right? So what's this? This is 32. But there's a standard piece of notation that we use to write this down, isn't there? This is power notation. So we could write this as 2 to the power 5. So this is just notation. It's just notation for this 2 multiplied by itself 5 times. And as I've just said, it's spoken as 2 to the power 5. Okay, so more generally, What's the story? Well, generally what we have is, well, if I was to do b multiplied by itself, let's say n times, well, who knows what that number actually is, but there's a piece of notation I'm going to use to describe it. I'll do it as b and then a subscript n. Okay, so let's make sure all of our terminology is correct. This b is called the base. It's called the base of this expression. And this n is called the exponent. It's called the exponent. Again, this is just notation for b multiplied by itself n times. And worth saying, in this case, n has to be a positive whole number. We'll see that n can be more broad later on, but at the moment, as far as we're concerned, this definition wouldn't make sense otherwise, right? If n was equal to a half, I mean, what does it mean to multiply b by itself a half number of times? It doesn't really make any sense. So this definition is exclusively about positive whole numbers as it stands. Special case, I mean, you could have b to the 1. What would that mean? That's just b on its own. B to the 2 is called b squared, b to the 3 is b cubed, standard notation. Okay, so what are we going to say here? Well, this b to the n business is not any of my other operations, is it? Right? It's not addition, multiplication, subtraction, or division. It's something kind of new. So let's give it a name. So conclusion. Repeated multiplication. Well, I'm going to call this exponentiation. It's a bit of a mouthful of a word, if I can even spell it. Exponentiation. So we're kind of defining what exponentiation is here, in a sense. Repeated multiplication, raising something to a power. All right. So as it stands, this b to the n business only makes sense for n positive numbers, positive whole numbers. Let's think about some of the properties that this notation seems to have. So important properties. Okay, so let's have n and m. Let's have positive whole numbers. So 1, 2, 3, 4, ... just like above. Positive whole numbers. So that means I can raise b to these powers now, right? It makes sense. B to the n times b to the m. Well, let's take a real careful approach to this. This is b multiplied by itself n times, then multiplied by, well, the same thing, b multiplied by itself, but now m times. Something rather nice happens now. If we think about it, how many copies of b are there? Well, there's n followed by m, so overall it's going to be the sum. So this is going to be equal to b dot b overall n plus m. So in this notation, something quite nice happens. This would have to be equal to b to the n plus m. Okay, so that's a nice notational property. Let's do another one. B to the n to the power m. Okay, so what's this? Well, this would be b to the n multiplied by itself m times. It's a bit of a monster. So what's this? This is m of these guys. But now each of the b's, or the b to the n, sorry, itself can split up. So let me try my best to write this down. So what do I have here? This is n of these now for each of them. And then overall, there is m of these. So in total, what does that mean? Well, there's n added to itself m times. So that's the multiple of the two. So this is b to the n times m. So nice. What do we have? We've concluded basically that the notation has these interesting properties. If I multiply together b to the n and b to the m, it seems to sum the exponent. And if I take b to the n and raise it to the power m, it multiplies the exponents. So those are kind of neat properties. So here's my aim. Let's come up with a meaning for, let's say, b to the n, even when n is not a positive whole number. So b to the half, b to the quarter, b to the minus 5, things like that. This is kind of an interesting thing. So really what I'm doing is I'm taking this notation and trying to come up with an extension of it. So just as examples, e.g., I've already said some, but here's some. N is equal to minus 1, n is equal to 0, that's not a positive whole number, n is equal to a half. All of those. So how am I going to do this? Well, I need to do it in a way that's kind of natural, sensible. And it strikes me that a sensible thing to do would be try to come up with an extension of this idea, but still keep these important properties above. So I'm going to try and do that. So here's going to be a requirement, an important requirement. Keep these above properties. So want to keep, what is it? B to the n times b to the m is equal to b to the n plus m, and b to the n to the power m is equal to the product. I want these two things to remain true. Whatever meaning I can come up with for these exponents, I want these to be true. So this is kind of an interesting way to go about this. I would imagine when you first saw exponents, you just had a series of facts told to you, and it wasn't completely obvious why the definitions were the way they are. But I'm kind of taking a bit more of a sophisticated approach where we have a very simple base definition for repeated multiplication, but it only works for exponents which are positive whole numbers. And then I'm going to try to come up with a definition myself where n is not necessarily a positive whole number, but I'm going to do it by demanding that these really nice properties still hold. Okay, so let's go through some potentials, shall we? This is a really nice exercise. So the first one, let's think what b to the 0 is. Right? Well, what do I want to be true? I want these properties to hold. And one of the things about 0 is I know that if I add it to anything, it doesn't change it. So what do I want? For example, if I had b to the power 1 times b to the 0. Okay, well, if I want these properties to hold, I would have b to the 1 plus 0 in the exponent. That's the first one. But then that's just b to the 1 again. But b to the 1 is b, so b times b to the 0 has to be equal to b, doesn't it? Okay. So at this point, I don't have many options. I just divide through by b. Something to be said, though, is let's assume that b is not equal to 0 here, right? So, oh, well, this would imply, so this would imply that b0 is equal to 1, assuming I can cancel off. Remember, you can't cancel off a 0. Assuming b is not equal to 0. So this is pretty neat, right? This tells us as long as b is not equal to 0, we know for sure what b to the 0 would have to be if I want this nice properties to hold. It has to be 1. So that's us saying, okay, this is the only option we can have if I want the above nice properties to remain true. Something to say is this is kind of a warning, for the base 0, we can't really do this logic, and it's a bit ambiguous what the meaning of 0 to the 0 is. 0 to the 0 is ambiguous. So what I mean by that is, Some people say it should be 1. Some people say it shouldn't be defined. So some define it as 1, some not at all. Some leave it undefined. Some leave it undefined. It's really up to you which you choose. I would prefer to define it to be equal to 1 for several reasons that I'm not going to get into, but it's kind of a bit ambiguous, so it's not so important. So really, overwhelmingly, the most important bases are non-zero, otherwise it's not going to be interesting. 0 times itself a bunch is 0, so we're not going to lose very much by losing this. Okay, so we've got b to the 0 now. It's going to be 1. Very nice. So I've extended from 1, 2, 3, 4 to 0 now. Can we go for whole numbers in the negative direction? So if now, let's say, n is a positive whole number, what would the meaning of b to the minus n be equal to? What would that mean? So again, we want my properties to hold. So we want my properties to hold, and what do I know about minus n? Well, minus n plus n is equal to 0, and I know what 0 is now. So let's try and exploit that. So b to the n multiplied by b to the minus n, that should be equal to b to the n minus n, summing those two. That's equal to b to the 0. Well, now that's equal to 1. So what does that tell me? Again, let's assume, so we're going to assume, we'll assume that b is non-zero, otherwise we run into trouble as always. So this implies what? This implies, well, b to the minus n should be equal to the inverse of b to the n. Very slick. So it's pretty simple. Right, it has to be equal to that. So I basically make that definition, right? That has to be what b to the minus n is equal to. So let's notice again here, there's a special case which is extremely important. Special case would be b to the minus 1. Well, now that's the inverse in ordinary fractional notation of b. Super important example. Okay, so let's do kind of a numerical example of this to make sure we're solid on it. So example, I don't know, 2 to the minus 3. So that's 1 over 2 to the 3. That's 1 over what? 2 to the 3 is 8. Another example, x plus 1 to the minus 1. That's equal to, well, just x plus 1. It's another way to write it down. Assuming x is not equal to minus 1, otherwise we'd have a problem with the denominator. You can't divide by 0, remember. Okay, nice. Nice and simple. So let's now do the most interesting potential. Let's think about what happens if I was to have fractional powers. So this has allowed me now to talk about b to the n for any integer. 1, 2, 3, 4, 5, 0, minus 1, minus 2, minus 3. Any of those, they all make sense now. What about if I'm dealing with some sort of fraction? So again, if n is greater than 0, a whole number, what is b to the power 1 over n? What would that even mean? So let's take a moment to go back up and look at my properties up here. We've only used the first. We've not used the second at any point. So what's the key thing about 1 over n? 1 over n has the property that if I multiply it by n, I get 1. So what does this tell me? Well, let's try to exploit this fact. So b to the power 1 over n to the power n. That would have to be equal to b to the n over n if I want my property to hold. That's b to the 1. That's just b. Okay. So what does this tell me? Well, whatever b1 over n is, it has to have the following property. b to the 1 over n multiplied by itself multiplied by itself n times equals b. That has to happen. So let me kind of talk a little bit about this property. So this is quite a lot more complicated than the previous examples. So any number, let's say r, with the property, or with this property, is called an nth root. An nth root of b. So more specifically, r to the n is equal to b is exactly the statement that r is an nth root. So b to the 1 over n, that's going to have to be an nth root, isn't it? Right? It's going to have this property. So a few pieces of terminology that are worth saying. If n is equal to 2, we don't say second root, we say square root. If n is equal to 3, we say cube root. And after that, we generally say fourth root, fifth root, sixth root, dot, dot, dot. Let's just do a quick example of this. Example. Well, notice that 2 to the power 3 is equal to 8. So that implies that 2 is a cube root of 8. 2 is a cube root of 8. Another example, 5 squared is equal to 25. That implies that 5 is a square root. Is a square root of 25. Okay, so we could go higher. I mean, just as another example, 2 to the power 5 is equal to 32. That implies that 2 is a fifth root. A fifth root of 32. So at this stage, I think we can conclude the following. So what have we got? Well, above we see that b to the 1 over n multiplied by itself n times equals b. That's got to happen. So said in this new terminology, what we're really saying is that b to the 1 over n must be an nth root of b. That's really what we're saying here. So the question is, what about nth roots? Can we find nth roots? Are there any thorny problems? Well, yes, there are some pretty serious problems. So let's think about the following. Let's think about defining b to the 1 over n. It's got to be an nth root. Now, the first thing is, if b is odd, if n is odd, then it turns out there are no problems. If n is odd, there is a unique nth root of b. End of story, very simple. So that means we're going to define this to be the unique one. This is the unique, and I should say unique real. The unique real nth root of b. So the unique decimal number that when I multiply it by itself, n times I get b. So just as a quick example, if we had -8, for example, and I was thinking about the cube root. Well, the only number multiplied by itself 3 times to get -8 is actually -2. So I would be forced to choose this is -2. There's no ambiguity, nothing at all. There's only one nth root. Brilliant, nice and simple. That's if n is odd. Well, what about if n is even? Well, this is actually very different. So there are two issues in this case. depending on if b is positive or negative. So if b is positive, the issue is there are two nth roots, a positive and a negative. Okay, so in this case, we make a convention. We decide that b to the 1 over n, I'm going to choose the positive of the two. The positive real nth root. Okay, so it does exist, but there's two of them. So just as a quick example, if I do 11 squared, that's equal to minus 11 squared, that's equal to 121. So that means I've got two square roots of 121. Plus and minus 11, we make the choice of the positive of the two. So this is decreed to be 11. Okay, so that's a convention, it's a decision. So there are two square roots, but when I write down 121 to the power of half, I choose 11. Now, even more seriously, if I have b is negative, well, here the problem is the following. If I take any number, positive or negative, and I raise it to an even power, it's got to be non-negative, right? 0 or above. So there's no way of getting b, right, if b is negative. So this tells you the only option really is to decree that it's undefined. b to the 1 over n is undefined. In the world of real numbers, undefined. As b has no nth roots, no real nth roots. So just as a quick example, all squares are positive. So let's say r squared is equal to minus 1 has no solutions. No real solutions. So that means there's no second root, there's no square root of minus 1, so minus 1 to a half, undefined. So this is it, right? This is the basic story about nth roots. If you're dealing with nth roots and n is odd, it's totally fine for any number at all, positive or negative, but the moment n is even, it's a bit subtle. You've got to be very, very careful. Okay, so let's expand on this a little bit, or at least introduce some notation. So let's think about the following. So rather than write b to the 1 over n, there's slightly different notation for this called radical notation. So radical notation is the following. It says that b1 over n, I might write it as the following. So I write this strange symbol. You'll have seen it before, I'm sure. To the n. So this is just notation. And this here is called the radical symbol, if you want. Okay, so a special case, one that you're very familiar with. B to the power of half, assuming it's defined. B to the power of half, assuming it's defined, is going to be equal to, well, you just drop the 2. So this is the positive square root. So by convention, this is always the positive square root, and you just drop the 2, as I said. Okay, so now what have we got? We've managed to take an exponent and make sense of it when it's an integer. So a positive whole number first, then 0, then negative whole numbers. And now things of the form 1 over n, where n is a positive whole number. So putting all this together, we're going to be able to define fractional powers, if you want, for any fraction at all. So case 1, case 2, and case 3, putting these all together. So using these, let's be a bit more correct. So using 1, 2, and 3, we've just gone through, we can define b to the n over m. We could basically do it in two different ways. We could define it as b to the n. So we've got to do it keeping my properties in mind. So it makes sense to define it literally like this. And we could equally define it like this, assuming everything makes sense. They should both be equal to each other, assuming they're defined. Let's do an example, shall we? So an example, let's do 27 to the power 2 over 3. So what's this equal to? Well, 27 is positive, so I've got no issues at all with square roots going crazy. Although it is a cube root, so it doesn't make any difference at all at the end of the day. But from one perspective, it's 27 squared to the power of third. It's a bit of a pain, though, writing it like that, because 27 squared is complicated. Let's do it the other way around. They're going to be the same. So maybe I'll just do this. And the reason I'm writing like this is I know that 3 cubed is 27, so I know that the cube root of 27 is going to have to be equal to 3. So this is going to have to be equal to 3 all squared, which is, of course, is equal to 9. So if you took the time to do this, this is equal to 9. Okay, so that just shows you some ways around, maybe simpler than others. So in conclusion, what do we have? We know how to define b to the n, where n is any fraction now whatsoever. Now at this point, well, within reason, you could have problems with negative b's, but if things are positive, if b is positive, then you've got no issues. So fact, if b is strictly greater than 0, we can extend this to define, say, b to the x for any real number x. So any decimal at all. It doesn't need to be a fraction. And I should say as well, something to notice about this, b to the x, I mean, if b is positive, b is just b to the 1 is b squared is positive, b cubed is positive, b to the 4 is positive. The negative versions of those, so b to the minus 1, to the minus 2, to the minus 3, those are all positive because they're just inverses of these positive numbers. When you go through the entire procedure of kind of defining b to the x for any x, it turns out that you always get a positive number out at the end. Strictly positive, it turns out. This is for any. It's just a nice thing to bear in mind, even if x is negative, right? Remember, 2 to the minus 1 is equal to a half, which is certainly positive. You run into tons of issues if you try to do this with b negative because of things like square roots of negatives. We kind of sidestep it entirely. So finally, there's one special case which is worth pointing out. If I have a base 1, not terribly interesting, but 1 to any power is always equal to 1 for any x. It's just a special case that's worth pointing out at the end of the day. So that is exponents defined very carefully. And just to recap, what was the logic that went into it? We started at the beginning thinking about what repeated multiplication was. We decreed that repeated multiplication was this thing called exponentiation, and we introduced this notation for it. Then we observed that there were certain nice properties that it satisfied. So down here, if m and n are positive whole numbers, these hold. So I asked myself, is there some natural way to extend this notation where the exponent isn't a positive whole number, but still keeping these properties? And if I do this, I'm forced into, first of all, defining b to the 0 to be equal to 1, then b to the minus n to be 1 over b to the n, and finally, b to the 1 over n must be an nth root of b. And that's a little bit complicated, but if n is odd, there's only one choice, so that's nice. If n is even, it's a bit complicated depending if b is positive or negative. If it's positive, you've got an nth root, but there's two of them, a positive and a negative one. You always choose the positive. And if b is negative, well, in the world of real numbers, there's no nth root, so that means there's no solution, so we just leave it undefined. Then we introduce radical notation, and finally, I suppose if we want to put this in a box, we define things for all fractions, assuming they're defined. And the last remark is, if b is actually greater than 0. You can do this for any exponent at all, though it's quite a bit more complicated, but the principles are all there. And the absolute last thing I'm going to say is that when I have the base as 0, it does make sense as long as the exponent is strictly positive. So the last special case is 0 to the x. This makes sense. This is equal to just 0 for all x greater than 0. So just as a quick example, something like the square root of 0 is of course just equal to 0 because of the fact, well, there's only one number that does this. 0 squared, 0 times 0. That's the only number that works, I suppose, by the zero product rule. So it works with any positive number. Negatives you can't do though, right? If I did 0 to the minus 1, for example, it would have to be 1 divided by 0, which doesn't make any sense because you can't have 0 in the denominator.